Hello, my name is Sergey Susher.
And I'm Nicole Hood.
And I'm Lane Worley.
Today we are going to be teaching you about the fundamental theorem of line integrals and the work done on a runner by the wind, given that the runner is a particle.
The magnitude of the wind in our demo is going to be 0.8 meters per second, and the direction is going to be coming northeast, 23 degrees northeast, with respect to the runner.
Now that we've got our field data, to the classroom!
To the classroom!
To the classroom!
Okay, so from the data that we collected, we had that the magnitude of the wind is 0.8 meters per second. So, and we're gonna call the distance, or where the runner ran, he went from 0 to about 100 meters. He ran 100 meters in just the positive x direction, and we're going to call that north. And this down here, this positive x with respect to the runner, we're going to call, if you look at it, we're going to call it east on the negative y direction. So we said also that we're going to have a 23 degree angle coming from 23 degrees north of east. So that's coming out here. You're going to have your x right here, and you're going to have your y right here. And so pretty much the force field, or the force field that the wind is going to make, you're going to have the force field being out here in the same direction at 0.8, or negative 0.8 technically, for each point that the wind is affecting it. In this direction, because it's 0.8 right here, that's going to be your hypotenuse here. And then to find the x direction, because the runner moves only in the x direction 100 meters out, we need to find the x direction that, or the magnitude of the x direction that the wind is exerting on the runner. So you're going to find x, given that sine of 23 degrees is equal to x right here. You have your opposite right here on your x, and then you have your hypotenuse equaling 0.8 as the magnitude of the wind. And we're going to end up with x equaling 0.3126. Alright, and because the wind is going this way from, say, you're calculating it from this point right here, you can say that the negative, the x direction is going to be negative, is going to be a negative work on the negative work on the runner. So we can say that the x is in the negative direction. So now we're going to use the fundamental theorem of line integrals to calculate the work done on the runner going from 0 to 100. And so we're going to have the fundamental theorem of line integrals is equal to the integral over the curve, or the line, of the gradient of little f dotted with dr, and that's going to be equal to little f of r of b minus little f of r of a.
Okay, so we have the force, which is big F, which equals negative 0.3126 I, and then plus 0.7 J plus 0 K, and then big F equals the gradient of F. So to find And then to find f, you integrate each part of big F or the gradient of f with respect to x and then y. So little f equals negative 0.3126 x I, then plus 0.7 y, j, and then plus 0, I guess, z, k. We don't really.
Right here we made a mistake. Little f is not a vector after we take the integrals of the gradient. We can actually write little f as a function and get rid of I and j.
Need that. And then since we're just, the y direction doesn't really matter, this cancels, and that's 0, and then we're not using z either. So, and then we need to parameterize the line, so then we have r of t equals 100 t, where t goes from 0 to 1. And r of t, this line, is the parameterization of the runner.
Now that we have all the data, we just have to plug it all in. So it's the integral from 0 to 1 of negative 0.3126 I plus 0.7 j dotted with dr, so it's dotted with 100 is going to equal f of r of b, and we our rb is equal to 1 and our a is equal to 0, so it's just negative 0.3126 of 100 times 1 minus negative 0.3126 times 100 times 0. This term goes to 0, and the answer is 31.26 negative newtons. And that is the work done by the wind on the runner. On the runner, by the wind. Wait. By the runner, on the wind. No, we can't.
By the wind, on the runner.
It's on the runner.
On the runner, by the wind. That is all. Have a good evening. Should be a sport. He's slowing down. He's tightening up.